Today, I want to go over some of the details of the problem that we looked at yesterday. This week, we are talking about flux integrals. The idea with a flux integral is that we are integrating a vector field over a surface. So integrating a vector field over a surface. And yesterday we made the point, since we're doing a vector integration, we're going to be dealing with a dot product. So this is going to be over an oriented surface. And we are imagining the surface as a bunch of normal vectors. This description of the surface as a bunch of normal vectors is still us describing a curvy thing with a bunch of tangents. We're imagining the surface as a bunch of tangent planes, and one of the ways we can describe a plane is with a normal vector. This means that we can describe the surface as a bunch of normal vectors. This is analogous to in a line integral when we describe a curve as a bunch of tangent vectors. So yesterday we had this problem, which was we had water flowing at 3 centimeters per second everywhere in a cylinder with a radius of 2 centimeters. Then we looked at a circle that is perpendicular. That circle is a cross section of the cylinder, so the area is 4 pi square centimeters. If we calculate the volume of water, the rate at which water flows through the cylinder, the flux through the cylinder, we'll just take the volume, the velocity, and multiply by the area. The velocity in centimeters per second, the area in square centimeters. That'll give us our the volume of water flowing through the cylinder per second, the flux. So we'll take our 3 centimeter per second velocity and multiply by our 4 pi square centimeters, spelled C backwards. So the flux through the cylinder is 12 pi cubic centimeters per second. The next involved a problem that we might not remember how to do. Calculate the area of an ellipse. Also calculating the area of an ellipse with the information that I was given, that you were given, is that the angle theta is between the direction that the water flows and a vector normal to the ellipse. So we put the theta in there. So we can go about this a few different ways. Number one, what we want to notice is that no matter how we calculate the area, however we calculate the area, the rate that the volume of water flows through the cylinder won't change depending on how we look at it. So looking at it at an angle like this, that shouldn't change the speed at which the volume of water is going through the cylinder. So it should be 12 pi cubic centimeters per second, regardless of what area the water is passing through. So if we have the ellipse, that should still be 12. So on one hand, this will tell us how things would change. There's a lot of ways that we can get at what we're looking for. That's actually my point. There's a lot of ways we can get at what we're looking for. So since the area has gone up, since the area has increased, clearly we can't use this 3 centimeters per second as our velocity of the water, because the area has gone up. If I just multiply by 3 again, I'll have more than 12 pi. So that means the volume going through the ellipse has to go down. If there is more area than the circle, then there has to be less volume, because the cubic centimeters per second shouldn't change. So the less than 3 centimeters per second that we want is the portion of the volume that's going perpendicular to the ellipse. We want the component of V that is perpendicular to the ellipse. So that tells us some stuff. If I want the component of V that's perpendicular to the ellipse, instead of multiplying two scalars, I'm finding the dot product of these two vectors. So I'll want to take the magnitude of V times the magnitude of A times the cosine of the angle between them. From a dot product as multiplication standpoint, this is where that cosine comes from. Since this 12 pi has to stay in balance, and I'm dividing my velocity by the, or multiplying my velocity by the cosine of pi, that means I'm going to be dividing my area by the cosine of pi. That's multiply by 1, divide by the other, divide one factor, multiply the other factor. And that's why we can conclude that the area of the ellipse is 4 pi over cosine theta. So if I grab the component of the velocity in the direction, or perpendicular, that's going to be 3 times the cosine of theta. And then so the area of the ellipse is going to be the area of the circle divided by the cosine of theta. Because the result still has to be 12 pi cubic centimeters per second. So here's where we find the area of the ellipse is 4 pi times the secant of theta if I move the cosine up top. So theta is whatever angle we put the ellipse at. So if we want to come at this from another perspective, we know that the area of a circle is pi times the radius squared, and the area of an ellipse is pi times one radius times the other radius. I know they're not radii, but keep calling them that. When A and B are equal, that means our ellipse is a circle, and we get pi r squared. Oh, to find theta? Yeah, we could calculate theta by dividing by using an arc cosine. We don't have a value in this case because it's still just theta. So the 12 pi doesn't help us because that theta will turn between 0 and 90 degrees. And when theta is equal to 90 degrees, then the cosine of theta drops down to 0, and then we have a problem. We can't divide by we can't divide by cosine of theta. So geometry-wise, we could figure out when we looked at the top view from side to side, one of the radii, A or B, one of them is just R. So if we look at things from the top, we take a top view. If we look at the top view, one value of A or B is going to be R, in this case, 2. So I could say A is equal to 2. Then I'll need to figure out what B is equal to. So in this case, A is equal to 2, and we want to calculate what B is equal to. For that, we're going to combine our top view with our side view. If we look at the side view, this angle in here is we've got the normal vector is 90 degrees from the ellipse. I've got this velocity of the water going along my horizontal, and I've got an angle theta between the horizontal and the normal vector. So we got to figure out where this theta is. So this theta here is, my conclusion is going to be, is going to show up here as theta. The way that we can get there is to look at these two parallel lines cut by this other line. We call that. We've got a 90 minus theta degree angle there. And so this angle is 90 minus theta. 90 degrees minus theta. Alternate interior angles, is that what they're called? Been a while since geometry. Alternate interior angles are equal. So if that in that right triangle has a 90 minus theta angle from alternate interior angles, then that means this angle up here is where the theta shows up. So that's the theta. Now, if I grab that right triangle with the red vertical and the ellipse as the hypotenuse, I've got this vertical is going to be 2r. My ellipse is going to slide down this way. as 2b. And then we're going to have the side that we don't really. Yeah. This is just the origin story for the 4 theta or 4 pi secant of theta. Modern movie storytellers has us doing prequel rather than telling the story in order. We got to be like, oh, where did all this stuff come from? It's like, oh, we'll give you a prequel movie, and then it's never good, except for Godfather 2. And then they're like, oh, I'm sorry I asked. So we can set up 2b as the hypotenuse and 2r as adjacent. So in this case, the cosine of theta will be opposite over hypotenuse, so that b, take out the 2, is equal to r over cosine theta. So b is equal to r times the secant of theta. So that's the origin story for the area of the ellipse being 2 times 2 secant theta times pi. This fits in with how we multiply. I want to calculate the velocity flowing through this surface. I need to know what portion of that velocity is flowing perpendicular to the surface. It's not that it's 3 in this direction. It's that it's 3 secant theta perpendicular. We need the component of that, the water flowing perpendicular to the surface. This makes sense that theta shows up here. When theta is equal to 0, then we get the circle. And we're getting 100%. Cosine of 0 is equal to 1. We get 100% of the velocity is going perpendicular through that surface. So here is where theta is equal to 0. I'm going to do degrees because I've got a trig class and I have to think in degrees otherwise. I'll start speaking radians. Yes. They don't make calculus with gradients anymore. Does anybody know what a gradient is? There used to have degrees, radians, and gradients. Anybody know what that is? That's how important it was. Incidentally, for those of you who are super pro decimal system, that's kind of where it came from. It's like, well, what if a right angle was 100? Then we all collectively agreed, it's like, oh, no, that is stupid. That's a bad idea. And we got rid of it. Like I was involved in that decision. I was the deciding vote. Right. So if we think about taking that theta and start increasing the theta, we know that we're increasing the area of our ellipse, but we're decreasing the flow perpendicular through the ellipse. When it's vertical, all of the 3 centimeters per second is going perpendicular to the ellipse. As theta increases, we get a little bit less as less and less of the 3 centimeters per second goes through the ellipse. When theta gets to 90, we have a super big problem because none of the water is going through the surface. When theta is equal to 90, our area becomes infinite, but 0 of the water is flowing through perpendicular. Area is infinite, but 0 is the component through perpendicular. Because we have to keep our ellipse stretches from this side to the opposite side, and it can't touch either one. So it's just infinitely long. This is a math cylinder, so it's infinitely long. And the engineer and the physicist like, oh, what about the curvature of the Earth? Like, oh, it's a math cylinder. This is in a Euclidean plane. It's flat forever. then the physicists and engineers are like, are you simplifying things to make your life easy? I'm like, oh, hell yes, that's exactly what humans do. We simplify things to make our lives easy. Unless we can pass on the difficulties to some other person. So the area is infinite. You think of this as the area is infinite. But also the perpendicular component so like 0 times infinity is 0. In this case, apparently 0 times infinity is 12 pi.
It's a number so long, times the number so big that it would come out 12 pi.
If I keep going, if theta goes past 90 degrees, is that 90? If theta goes past 90 degrees, then the orientation of our ellipse has flipped over. Here's theta is 90 degrees. Past 90 degrees, our normal vector is going against the flow of the water. So our component perpendicular relative to the orientation of the ellipse is negative. But those negatives will cancel out, so we get 12 pi cubic centimeters per second. So when theta is past 90 degrees, the component perpendicular to the ellipse will be negative. I was thinking I needed to draw this all the way across, and I'm like, oh, no, I don't. And now I just realized, yeah, I did. So for theta greater than 90 degrees, the normal vector now going the other way. So the component of the velocity that is perpendicular to the ellipse is negative. But then when we calculate the area, that also works out negative. So our area is negative, but the perpendicular component is also negative, so they cancel out and everything's okay.
So any orientation still has to come up to 12 pi.
Still works out to 12 pi. The two negatives cancel out. All the way up to theta equals 180 degrees, in which case the orientation is exactly the opposite of the flow, or the exact opposite of the velocity, and the negative one cancels out with the other negative one. Any questions? Is everybody okay? Everybody looks super stoked.
We kind of mostly saw this.
This is just going over the details. We had the answers yesterday. This is just kind of recapping the details. We're just taking some time to make some notes today about stuff that happened yesterday. We might have known that the area of an ellipse tilted at 45 degrees from the vertical is going to be 4 pi, or pi times r secant theta. But now we can see where it comes from, so we don't have to remember that. And we can actually know that. Is everybody okay? This happened in week 3 of physics. I feel like I'm late to the party then.
Is it physics one?
Which physics? 260? That's the electricity one, right?
Oh, yeah.
So they're like, well, now you tell us. Did you actually have to calculate integrals in physics?
Yeah.
We're like, add 1 to the exponent, divide by the new exponent? Always get rid of the integral if you can. And if you can't get rid of the integral, find a way to ask a machine about it. That's why we have them. How's everybody okay? Funny, because now I'm thinking it's like, well, when was the last time I was in a physics class and I actually had to do math in pursuit of physics? And it was a very long time ago. It was like the early 90s. Any questions, comments, snide remarks? So wait, so the 251 get you to 2, then you can do 2, then physics. Then if you do math, then you do physics 250. Is that the first one? So to do physics 250, you need calc 1. While you're doing physics 250, you do math 252, calc 2, but you're still single variable. Then from physics 2, after physics 250, is 252 a prerequisite for physics 260? Okay. Yeah, or at the same time. Okay, so you can be concurrent 260 and 253. You have to be concurrent because in math, you'll talk about flux integrals. And in physics 260, you'll be doing flux integrals, but it's completely backwards from your actual experience with the thing. That was revealed to me yesterday. What is it about that what you've written on the board reveals to me yesterday that you'd already been through flux integrals? It's the capital phi. Once I saw capital phi show up, I'm like, oh, how long have you known about this? And no one told me, but that's fine. That's fine. So this is when you get to do math 253, learn about flux integrals after you've seen them in physics. And it's like, well, LOL, I'm late. Oh, you can do those out of order? Do them at the same time? That's fucking hardcore. One strategy I know students used to do is like linear algebra and differential equations, or your first differential equations class, at the same time during the summer. That's hardcore. It's actually not that hardcore because linear algebra is pretty easy. Of all your lower division math classes, to me, that one is, because it's linear, right? Everything's flat. Everything's going to be flat and Euclidean forever in all directions, then it's going to be all right.
The world still makes sense.
But then it's also hugely variable. All right. I really just wanted to go over the details of why we had our area of ellipse at 4 pi secant of theta. I wanted to make it clear where this theta shows up as far as the angle as we rotate this circle into an ellipse to a flat plate and then ellipse going the other direction. So that I really wanted to emphasize the fact that this surface has an orientation to it. So that the water, once we get past 90 degrees, mathematically, the water is flowing through the wrong side of the ellipse. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.